Thanks very much. It's a pleasure to be here with you all. I was on the bus with everybody today and got to embark upon the viewing of the rocket and everything else, and to stand there and look at it. For those of us that have been working on GOES-R kinds of stuff for the last couple of years, in my case, since about 2008, it's good to see. So we're really excited about tomorrow. Again, I'm from the Weather Service Eastern Region Headquarters, Scientific Services Division. What we do is to help facilitate and lead training and data usage as part of the forecast and warning process for our weather forecast offices, river forecast centers, and CWSUs, the folks that work directly with the FAA. And so I'm going to come at it from a little bit different perspective today, but my focus is basically going to be on what we've been doing to prepare for utilization of GOES-R information as part of the forecast and warning process, and ultimately to provide impact-based decision support services that you heard a little bit about earlier today. First, a couple of acknowledgments. Frank Alsheimer, who is the Science Operations Officer at the Forecast Office in Columbia, was supposed to give this talk. He is actually out in Kansas City right now at the Weather Service Training Center teaching other science and operations officers about GOES-R. And so he put together quite a bit of the content that we'll see here. The others on this list, Dan Lindsay and Tim Schmidt, again for multiple years of access to GOES 14 data, which we'll talk a little bit more about, and how that's helped and continues to help the Weather Service prepare for the 1 minute temporal frequency. And then the rest of the folks up there contributed some cases that we'll look at here as well. You heard a little bit earlier today about IDSS. Again, impact-based decision support services. This is kind of the new paradigm for the Weather Service, and it's really about providing detailed, accurate, critical information to enable folks to make decisions. That's really what this is all about. So in some ways, it's enabling folks to make better decisions on our information. And so GOES-R clearly is going to help us do that in the sense that IDSS really hinges on a good forecast. Credibility and everything else sort of are part of that. And if you don't have good forecasts, the IDSS piece makes that a little bit more difficult. So in terms of helping us make forecasts and observe things that are currently happening, IDSS is going to come a long way in helping us to do that. You also heard a little bit about the Weather Ready Nation, building community resilience. Again, if you are not a Weather Ready Nation ambassador, I encourage you to work with your local forecast office, media workshop and whatnot to become a WRN ambassador. You folks are the face of the public in a lot of ways and can help get the message out as we continue to try to build community resilience. Here's some images from Hurricane Matthew up here, and again, the sort of obligatory trees across the hurricane evacuation route there in the bottom. That's kind of where we're at there with the Weather Ready Nation. So again, this is a strategic outcome. You saw this picture earlier today on the left here, and this is from Hurricane Matthew. The gentleman there on the far left is the warning coordination meteorologist from the Columbia Forecast Office in the State Carolina Office of Emergency Management, right there with the governor, helping to provide information as they continued to work their emergency operations during Matthew. Okay, so the way that I want to treat really the rest of this discussion is to try to take a look at how we have worked in the Weather Service for the past several years now, getting ready for the improvements that we're going to see both temporally, spatially, and spectrally from GOES-R. And what I consider to be maybe the more simpler one in some ways is the temporal resolution. You've seen some images, Tim showed a bunch from GOES 14, really since about 2012, maybe early 2013, since Sandy essentially. Weather forecast offices have had the ability to pull in the GOES 14 1-minute data into their AWIPS. And as an experiment, sort of an experimental product to get used to using 1-minute imagery in their forecast process. here's an example of that. One of the big benefits, of course, that you saw from some of the previous talks is convective information, looking at and interrogating cloud top temperatures, looking for where convection is initiating and, of course, growing as we think about severe weather. Maybe one that sort of gets a little bit lost is looking at boundary information. So 1 minute information in terms of boundaries, if you consider where I'm from on Long Island, we have a couple of airports around and a sea breeze. When that wind direction shifts at any of those airports, that oftentimes will require a runway configuration change. And so being able to provide the FAA and the folks at the TRACONs and the airports information about when we expect that to happen with a little more granularity kind of helps them will help them in their operations. And it's actually amazing how many times you see the sea breeze push north of Kennedy Airport and hang right south of LaGuardia. But for those kinds of boundary information, looking at the use of this better temporal information is certainly going to help us out there. And I clicked on something. Okay. And of course, both development and dissipation of low clouds and fog. And you saw a really nice example of that from Tim's talk today. In terms of fog, it's not only, of course, the formation of fog, but also the dissipation of fog in terms of transportation. Fire and smoke dispersion, of course, is also important, and we'll talk a little more about that. Again, this is, I think, where we are going to have the most challenge, just based on the quantity of information, is with the 16 channels. So again, we're going from 5 channels to 16. And then when you start considering all the different combinations of channels, whether you're channel differencing and combining, the permutations of imagery that one could actually produce gets large very quickly. And how to use that effectively to help make forecast and warning decisions is something that's going to be very interesting to see going forward. And I think Greg Mann actually today mentioned the fact that we're going to see things coming out that we're not expecting now. That's pretty much a given in terms of utilization of this information as part of the forecasting warning process. But what we've sort of identified so far in terms of looking at the additional spectral information that comes out of that will come out of GOES-R, elevated mix layers, sting jets, and then again with the additional water vapor bands, some additional information a little bit lower in the troposphere to be able to discern things like excessive precipitation. And then, of course, your multi-channel products, which again goes back to the channel combination of RGBs that we call, we'll be able to tease out and bring out some better visualizations of phenomenon. So again, all this feeds back into better forecasts, better observations, better information for use with our partners and customers. Spatial resolution, again, going to 2 kilometers for the infrared at nighttime is actually going to be a pretty big deal, I think, as well. It's going to allow us to see things at night in terms of convection in particular, that I think is certainly going to help us in terms of warning operations, valley and river fog, and of course, Steve just gave the great talk there on the GLM. I'll talk a little bit about that. But again, lightning initiation and, of course, use in other products in terms of public and aviation safety. So pretty exciting things to look forward to there in terms of the GLM. Okay, the last couple of slides talked basically about using satellite information as an observation. And we would be sort of remiss to not discuss a little bit about what I'm calling the indirect benefits. Indirect isn't really the right word, but it's basically the use of satellite information in other products that help us make a forecast. And so the first example of that, which Steve showed and was discussed a little bit before, was the big experiment that we just got done running at the Weather Service over the summer using ProbSevere. Here is a probabilistic product that can give potentially warning forecasters more confidence in issuing a warning or in canceling a warning. And you can see here, all they are little shape files that circle. It's an object that circles the cell. And you look at the trends and the probability. But this is sort of called what I call a data fuse product. So in other words, it's using cloud top cooling and some other sorts of things, including lightning, model background from the RAP and some other sorts of information, MRMS data, for example, to produce this information. So this isn't GOES-R data proper, but it's using some of that information to produce something else that's useful within the forecast and warning process. Obviously, assimilation into operational NWP, the GFS, the NAM, our operational suite of products is going to take advantage of GOES-R information and the rise of simulated satellite data from models. And one example here, again, this is over the busy New York airspace. This is the, I think Steve showed this as well, but this is an example of the what we call the fog and low stratus and the probabilistic flight category. So again, in terms of supporting aviation, when we're looking at the probabilities of certain flight category conditions, this is a particular product here that our folks are using to help inform the FAA and others of impending flight rules, for example. And the rise of simulated satellite data for models. And again, as we've been preparing for GOES-R, since we don't have real data to work with, at least over CONUS, we've sort of gotten accustomed now to looking at simulated satellite data from the models that sort of emulate the bands that we can expect on GOES-R. So that's gotten a little more use based on what we've been doing in preparation as part of the proving ground. All right, let me take you through just a couple of examples here now of sort of how over the last few years we have been using, in the first couple of cases here, some of the GOES-14 Super Rapid Scan 1-minute imagery. Again, the motivation here was to expose our folks to the 1-minute frequency in preparation for GOES-R. And so we were lucky enough to be able to do that with actual data, not having to use either Himawari or proxy data from a model, for example. All right, so this example, we have two small examples here really from the same day. So we call this is the North Carolina example here, part A. Typical May day, a couple years back here, with large hail, moderate to weak instability, seasonably reasonable lapse rates, et cetera, and the initiation of the convection really began with an MCV. And so the 1-minute data was used by the forecasters, in this case from the Raleigh office, to track the MCV as it moved across overnight and into the early morning, the southern Appalachians, east of the southern Appalachians. Convection initiated, dissipated, and then re-intensified early, mid-morning in central North Carolina. So that's kind of the scenario that we're looking at here. And again, for comparisons, and boy, these sort of comparisons don't ever get old, do they? Left-hand side, again, there's North Carolina, South Carolina, and Virginia there as you go from top to bottom. But you can see GOES-14 1-minute on the left for the visible, and GOES-13 legacy 15-minute on the right. And you can see a little, it's hard to point here, but you can see the MCV sort of traversing there. There we go, as things go through. So we'll let that play one more time. And you can see the convection begin to fire right there, kind of along the northeastern periphery of the MCV. Taking a look again, this is the 1-minute data from the IR channel. Again, the spatial resolution is not what we're going to have with GOES-R, but just to give you a sense of what it looked like on the 1-minute versus the 15-minute. And the radar depiction, oh, this is going to work, excellent. And the radar depiction of the cell that forms right there. The convection dies and reforms there along the edge of the MCV. If you kind of take a look at some of the elements that one would look at that's working the radar that day, again, we have a 4-panel here, time 1-minute increments along the x-axis, and then yellow bars in each of these indicates when the warning was issued. The red indicates when the first storm report was issued. You see here, in this particular case here, you can see, again, the 1-minute cloud top, if you were to sort of sample in and around where the convection was along the MCV there, you can see the pretty quick ramp up here in cloud top temperatures, within the span of about 5 to 8 minutes. VIL looks pretty good, and the height of the 60 dBZ echo there ramps up pretty quick as well. So in this case, at least, you can start to see early on convective initiation and the rapid cooling, at least, of the cloud top temperature. So again, just to sort of reiterate here, the 1-minute data was used really to track the MCV, with a little more confident. Again, if nothing else, the 1-minute data for sure lets you know that, yes, the atmosphere is a fluid, and things seem to behave in that fashion, more so than with the GOES 13 15-minute data. Again, the 1-minute imagery, as we'll see in a couple of these other cases, really is used to identify areas or cells early on that show convective initiation promise. I guess maybe that's the way to look at that, where we have developing cumulus that could signal better growth and sort of focus your attention on one of these locations where then you may want to start more in-depth radar interrogation. Prior to the warning issuance, the rapid convective growth, and this thing produced some large hail a little bit later on there in Moore County, North Carolina. Later on that day, further to the south, as the main front came through, again, GOES 14 on the left, GOES 13 on the right. You can see another cell blowing up over Greensville-Spartanburg, this area there, kind of in western North Carolina, making its way to the east. So again, this is later in that same day. This guy does, in fact, you can see again from the 1-minute visible. There it goes, right up over Greenville. The radar depiction as well. And in this case, when you take a look again at the 4 panel here, again, time is on the x-axis. Your yellow bar there indicates the warning issuance, and the red, the 2 storm reports that were received. A little bit different scenario in this case, where you basically see a pretty clear trend, at least in interrogating the cloud top temperature in the 1-minute data, whereas the VIL and the height of the 60 dBz don't give you quite the same clear-cut cloud growth or growth of the system. And so in this case, when you start looking way, way back in the early times here, you're watching that thing in the 1-minute imagery cool pretty quick and grow pretty quick. So again, a little bit more information, perhaps in this case adding a little bit more confidence to, yeah, this is the cell that we need to be paying attention to, particularly when you're in one of these situations where you have multiple cells going on in your area. And actually, on this particular day, SPC was watching the same thing in terms of the 1-minute data, pointing out the additional clumping of Q in that area as well before they put out their severe box. And here's the reports, basically from South Carolina, mostly hail, as you look up there to the north and the west of Columbia here, back in Greenville-Spartanburg's area. Okay, so again, one more example of the 1-minute imagery, another severe thunderstorm example. This time we're going to go up north into areas where we have radar coverage, some sparse areas of radar coverage. And in this case, the 1-minute data supported warning operations in an area with radar coverage that wasn't so great. And again, what are we looking at? It's the rapid cloud top cooling. And in this case, when the cell had moved far enough into an area where the radar coverage wasn't that great, they actually continued the severe weather warning when it may have been canceled if you were going solely by radar. So again, utilizing this very high frequency information when you see that things are still rapidly growing. And so we're going to start this, and you're going to be watching this cell right here. And again, if you look off to the east, you can see the low-level flow. And we take a look on radar. And there you go. And I think at this particular case, the height of the radar beam, at least at half degree, something like 11,000 feet or something. So it's pretty high. Okay, one more example, I think, of the 1-minute imagery. This, again, we're going to go back to the east in South Carolina. In this case, we're looking at a boundary. So other than sea breezes, again, taking a look at synoptic boundaries, in this case, a very slow-moving boundary. And if conditions are right, in other ways, of course, for training of cells or back building, you may be looking at a case of flash flooding depending on where you're at. And so identifying and tracking the boundary, again, when you're looking at 15-minute chunks or even 7 or 8-minute chunks in the current GOES rapid scan. So when we call for rapid scan now, it's about on the order of about 8 minutes. Having the 1-minute information and looking to see what's happening or what isn't moving is really the key here. So in this case, location of the boundary we're looking at to figure out and determine the upshear movement of convection. And in this particular case, over the Charleston, South Carolina metro area, which is pretty prone to flooding, given obviously its location. So here we go. Again, GOES 14. Watching this right here, and just look at the difference as you watch things begin to propagate back to the west. I can't find the cursor again, but again, you're looking right in here. Okay, same thing. Again, taking a look, even though we have the coarser spatial resolution here, taking a look as to where the coldest cloud tops are, and watching this in a 1-minute thing, at least, temporally, you're given a little bit more information in terms of looking to see where things are backbuilding. Again, the radar depiction here is going to show the same sort of thing. We'll let this play for a moment. Again, here's the Charleston radar. Here's Charleston proper. You can see the backbuilding, the outflow boundary that begin to move as this stuff continues to backbuild through the afternoon. Hard to see the background underneath this, but the rainfall, so Charleston is right in here. Rainfall reports in the gridded overlay here show basically anywhere from about 1.5 inches to over 3 inches. From this event, most of that fell in about an hour to a little over an hour. And so reports from that in terms of the flooding and that sort of stuff, there you go, just north of Charleston, a over 3-inch report. So again, in this case, kind of monitoring the movement and the sort of backbuilding of this convection during this flash flooding event down in Charleston. Okay, the GLM, again, Steve covered this in pretty good detail, but again, I'll just point out, similar to what he showed, if you're looking at, and again, this is using the Colorado Lightning Mapping Array, the Colorado LMA, which we are using now, at least in the east and the DC area, to sort of emulate the GLM. You can see here that you have some lightning activity reported in an area kind of far to the east of where the cores of the storms are. So here's a case where it's not, another case where it's not necessarily a bolt out of the blue, but you do have lightning activity in areas that are not as convectively active as you might think. And so here you go, on the order of 40 miles away from the cores of the storm. And so in terms of knowing where this information is, if you are, if there's some event going on, outdoor event, if we're providing support for some outdoor event and the emergency management folks in that vicinity, that's information that we'd want to know, which again is out well ahead of the convection. Okay, another example here. This now gets back to away from the sort of spatial, or the temporal rather, information in terms of looking at the 1-minute imagery, but goes now more towards the multispectral. So again, we're going from 5 channels to 16 channels with GOES-R. And how are we going to utilize this data in terms of making forecasts? So here's an example from a couple years ago. You may remember from the Northeast, tornadoes there on June 1st. There were something like 4 tornadoes, over 1,000 homes damaged, and a pretty big day for up there, including the Springfield event from that day. And so we'll show you here how some of the multispectral imagery, at least from current GOES sounder data, could have been used in terms of assessing or better assessing the role of the elevated mix layer. But you can see here on the morning sounding from Albany, pretty good dry layer there from about 700 to 550. Really nice shear there in the lowest kilometer in terms of speed shear, good directional shear all the way up. And you can see as you take a cross section from Albany back through about Rochester, the upper level front occurring there. So the 7.4 micron in the current GOES sounder. Okay, so again, every 3 hours, very coarse resolution, in terms of trying to track where that upper level feature, in this case the front, is. Imagine doing that every minute with a 7.4 micron, or approximately 7.4 micron water vapor with GOES-R. Be able to track that in much more real time. But one of the ways that we've been trying to take a look at some of these new channels with the ABI is through looking at current sounder imagery and, of course, through some proxy data as well. Another example here from the southeast. Again, one of the ways that I mentioned we've been preparing, again, for the new bands on the ABI is through some of the simulated channels from model output. So here we go. Our area of interest here is going to be in South Carolina. You can see the area is caught between an upper low here, some pretty good moisture, and an upper low back to over the North Gulf of Mexico. And folks that day were sort of anticipating convection once again. And so how did they use this information to help make a forecast that day? Well, if you were to look at the traditional or the currently available water vapor imagery in AWIPS, let's say, you're looking up a little bit higher. You can see here pretty good moisture, it looks like, over much of the region. So you might think that for a lot of the area, pretty heavy, heavy precipitation, convection is a possibility. But when you start to look a little bit deeper, you look at some of the sounding information, you can see that there's a dry punch kind of moving in here, north of the upper low down here, into the area. And so there's a boundary, at least in the lower levels here, that's sort of developing Charleston and west. And so again, the idea here is convection or not on this particular day. And as it turned out, most of the convection stayed pretty well to the west of the Charleston area in terms of long-lived rainfall and convection. And so when you look at where the radar estimated rainfall was for this day, everything occurred pretty far west of that demarcation line in the moisture imagery. And so think about, in terms of providing IDSS kinds of things, sometimes relating when things aren't favorable to happen is just as important as relating when things are going to happen. So here's a case where this information, and you think about GOES-R, and when you have much more finer, detailed, lower level water vapor information, we can better assess, in this case, the fact that most of the precipitation was going to stay to the west of Charleston. Okay, AMVs, mentioned a little bit. This is pretty exciting as well in terms of when thinking about using 1 minute information to produce AMVs. Here's an example here from Himawari, again, the Japanese satellite that's similar to GOES-R. You can see the difference in what the AMV density is going to look like, in this case, for a tropical system. And when you think about the fact, really, that what emergency managers want to know is when is the worst going to hit? When can we expect the conditions to be the worst? And when you have detailed data like this, you can almost pick out the mesovortices and everything else within this system with AMV density like this. So we are really looking forward to the increase, obviously, in the data quality and the quantity for the AMVs that we're going to get from GOES-R. So that's one of the things that we are certainly excited about. And again, this information then also gets fed into the numerical models. And so we will see that downstream in looking at model guidance as well. And again, here's just an example of what that would look like from Hurricane Ike from a couple years ago. And in this case, you can see the red here showing the outflow at the top, and the greens and the blues a little bit lower in the atmosphere as you get out away from the center of the system. So these AMVs, we think, are going to be a pretty big and pretty exciting thing for us to be able to use in real time here as we go. Okay. A couple of additional examples of what we're calling sort of the multispectral things that we're going to be able to see with the multiple channels. Really, that's, if you want to sort of phrase it in a simple sentence here, a couple of sentences. Here's an example here of some dust coming off the Gobi Desert, but you can also see this is a geocolor image, and so what you're going to see towards the end there is the day transitioning into night. And so you see underlaid below here in the last couple of frames, right here, the northern lights, the lights, which is a static image from the SNPP polar orbiter. You can see South Korea here, and again, most of China. But again, this gives you a seamless sort of picture from day into night of clouds, but in the daytime at least, looking at the dust transport. So for all you that are from, West Texas, some of the places with a dry line out west, imagery like this, which basically, again, this is a geocolor image produced by the folks at Colorado State that takes multiple imagery and combines it into one, allowing you to see different phenomenon. This is just a new way of visualizing satellite information, and in this case, with a seamless transition from day into night. But you can pick out the dust pretty well here. Smog example, again, when we think about IDSS and impact-based decision support, it's not necessarily just about, sort of the traditional, tornadoes and hurricanes, but we think about things like air quality, heat and cold, and other sorts of things that do have a real impact on folks. And so again, you can see here Madagascar kind of in the center of the screen, and then back to India to the west, and Nepal up there. But again, you can see things get trapped. You can see towards the end here, stuff get trapped in the valleys, and just the in this case, the amount of smog there is actually pretty impressive. But again, another example of a geocolor as we transition into night, ways of looking at this information. I don't speak Icelandic. I tried to pronounce this about 10 times. Everybody remembers this from a couple years ago, from the Iceland volcano that produced the ash clouds, plural, that hosed up the international air traffic for several days. But again, new techniques to visualize using multiple channels. In this case, the black cloud you'll see kind of float across there, giving us more insight, and in some cases even earlier, in terms of being able to observe where this stuff is. That information gets fed into, in some cases, into numerical models, and then forecasting where this stuff is going to go. So, new visualization techniques as we get into these multiple channels. All right, smoke over Russia. I think this actually may be the one that Tim showed. Look at this. I mean, you can see it get caught up. I count probably a dozen or more individual fires there. And again, this is another example of combining multiple channels to take a look at particular phenomenon. And so, having this available, even now what we're seeing in the southeast, to help with smoke and IDSS kinds of things. Again, yet another example, in this case a mid-latitude cyclone. Look at the open queue. Does this stuff ever get old? You can see it there as it makes its way towards the west coast. But pretty good example there, again, of another. This is a Himawari shot of a couple of minute data in their rapid scan. And then finally, again, keeping in mind, these zoomed in kinds of things. This is just from a couple months ago. Look at the detail here, and this gets to the spatial piece as we take a look at, in this case, Himawari rapid scan is 2.5 minutes, but looking at their visible channel as this super typhoon impacts Taiwan. And just looking at the, again, going back to the question of when can we expect, from an emergency manager question, so to speak, when can we expect the worst of the conditions? Again, using this high frequency, high temporal resolution information as part of our forecast process is really going to help us. Do that better. And I think that's the last slide I have. I did go a little quick, just given that we were so far behind. But at that point, I hope I've given you at least a little bit of clarity into what we have been doing on the Weather Service side, particularly at the forecast office level, to try to get a hold and prepare our folks the best we can for the onset of this exciting new data set coming down after tomorrow at 5:42, plus a couple months. Thanks. I don't know, Dave, if we have time for questions or not, but
I think we should take some questions.
okay.
Anybody that has questions?
Please raise your hand, and then I'll call on you and just turn on your microphone and identify yourself. Go ahead.
Nick Stewart, KHQA, Quincy, Illinois. Kind of to play devil's advocate for a second, has anything kind of been discussed regarding, like, you're going to have these updates so quickly, like, kind of having some weight, issuing a warning, for example, if like, it's like, oh, let me wait one more scan, because they're coming in so quick. Has there kind of been any discussion on that about, like, how long would be too long kind of thing?
No, I mean, I think it's going to take some time for our folks, Weather Service wide, particularly for the 1-minute data, to be able to routinely use it. So we've had offices that have been looking at the GOES 14 stuff through the 2-week periods, and then it's gone. And then it comes back again 3 months later, then it's gone. But for Weather Service wide, I think it's going to take some time. Now, you have an ability within AWIPS to skip frames. You can do all sorts of neat things with time matching, or basically slice and dice any way you want. So if you want to skip every other image, you can do that. So I have a feeling it's going to be up to the individual forecaster, purview to do that, knowing that, of course, the 1-minute data are always, will be there, and it's going to be up to them over time to sort of build that into how they work warning operations.
Mike Mogul, Naples, Florida, how the weather works. I've been in the National Weather Service. I've had to put out my share of warnings and so forth. I too don't want to throw cold water on this. This is awesome stuff. But I can see the scenario where we're faced with, gee, the storm's weakening, I'll cut the warning back. Suddenly the storm re-intensifies and I have to reissue it. It could work cross purposes. I'm also concerned that we now have some parameters we're looking at, like rapid cloud top, temperature change, et cetera, et cetera. What about the false alarms? Every case isn't going to work that way. It would be good to present perhaps a more realistic scenario that here's a good case, here's one where it didn't work type of thing, so we don't oversell it.
No, you're right. And I think that first case from North Carolina that I showed would be the best example of maybe not as much utility as the second case in terms of looking at something as specific as the cloud top temperature. When you think about all the tools that we have in terms of things like ProbSevere, there's a lot of information coming in all at once. This is going to take some time. But yeah, there are certainly cases where we have, and I think, again, the North Carolina case, maybe an instance of that where the using cloud top cooling alone certainly is not, did not necessarily add much benefit to the warning process, let me say that.
Erica Groh, WNBC. When I went to the hazardous weather testbed a couple years ago, we loved ProbSevere. We thought it was great, super helpful. I get the impression that different WFOs will use it differently. It's almost like as if they'll have to calibrate it for their own climate and their own region of the country. But, it never occurred to me when I was out there to ask why now? Is it because the data is so much better with GOES-R that we can utilize some of these derived products? Because I can't imagine that ProbSevere and some of these other things, like they didn't exist beforehand, right? So what's the deal with that?
Yeah, two things. Number one, back to your hazardous weather testbed experience. I'm glad you got to go to that, actually. These are probabilities. And so the output from ProbSevere gives you a number, along with some elements, parameters that have gone into producing that number. Part of the challenge with using ProbSevere, and again, we look at it as a decision aid, so something that adds a little bit, that can potentially add confidence to issuing the warning. Part of it is folks or forecasters getting used to, 70%, 76%, 92%, 68%. Is it a function of regime? Is it a function of convective setup? Self-calibration over time, yeah. The folks that have developed Probsevere have done some work in looking at stats based on the probabilities that come out over the last couple of years. And it seems to show pretty good reliability. Again, I think it's one of those things. It's not an operational product. I need to be clear about that. Again, this is an experimental product that we've been working, that the folks at NESIS have been developing. We've been helping out in terms of evaluating as part of the forecast and warning process. But I think, over time, calibration and understanding about when this works well versus when it doesn't has to be, teased out a little more specifically.
But what I'm really asking is it because of the advances that GOES-R provides that we're able to even use a product like that?
Yeah,
Or is it a coincidence that they're both coming to fruition at the same time?
Yeah, I think when you start to have multiple scales, both in space and time of numerical, so again, this is also using high resolution modeling. They'll be transitioning to the HRRR. In addition to the high frequency of temporal frequency of the satellite information. It's being used right now when GOES 14 is not running with, GOES 15 data and 13 data, so 15-minute information. But yeah, it's a convergence maybe in some ways of disparate data sets, so that phrase data fusion that I used, where you have multiple data sets, both gridded, other observing platforms, again, MRMS is an input, MESH, if you're familiar with that, is an input into Probsevere. So you have a bunch of variables coming from different sensors, gridded, observed, and otherwise, that are all now of about the same temporal and spatial scale. So I think there's an opportunity there to take advantage of that. And it also cuts down a little bit on, you think about all the data that are out there right now. This idea of data fusion, if we have, if we can combine some of this information into one thing, does that help? Does that get us, an answer maybe a little bit quicker than we might otherwise? So there's some, some benefit to that, I think, as well, in terms of reducing the amount of things that we're looking at all at once, especially when you're in warning operations. So, yeah.
Additional questions? Anyone else? Okay, that sounds great. Thank you so much.